So, welcome back to COMP526, and welcome to a new exciting unit, Unit 4, where we'll talk about string matching. And because string matching sounds very academic and not very useful, I put this subtitle here, because unless you're on Mac, and I don't know what the command is called there, pretty much throughout all programs you can press Control F, and it gives you some ability to search. And that's really what we're doing here. We're explaining what's happening there, especially if this is a text editor or a browser where this is essentially text-based. And we'll come back later to the scenario that's closer to search engines or indices. So learning outcomes for this unit, I want you to be familiar with the theoretical notions and notations for strings. This is just something, again, I think computer science tend to communicate in these terms, so it's important to know those. And pretty much anything is a string, so they are ubiquitous in various ways in programming. But we'll take the mathematical notations into this game as well. I want to introduce three main algorithms, nicely abbreviated so that they don't make much sense if you don't know them, but that's Knuth, Morris, Brett, Boyer, Moore, and Rabin Karp, all named by their inventors. And apart from just knowing how they work, I want you to know what the differences in their performance are. It's a little bit like in sorting. None of them is completely dominating the others in all possible metrics. And instead, you'll have to sometimes mix and match a bit, depending on what you need. And lastly, it turns out that a component of KMP can be used for solving more sophisticated problems than just finding occurrences in a text. That's what string matching is, by the way. We'll come to the proper definition in a second. There's something more versatile going on, and so I want to teach you a little bit how this works, but nothing too crazy. I broke it up in nice little chunks, but some of them will be quite quick, in particular the first few. And we'll talk about another method that leads up to KMP first. That's string matching with finite automata. With that, let me start with the introduction, and in particular, all this notation around strings. I'll jump through some of these slides a bit quickly. They're both mostly for your reference. So first of all, what is a string? And we're not talking about underwear. It's a sequence of characters for us. And the characters can be something we'll talk about in a second. I want to first stress how ubiquitous they are. We use them for natural language texts in one form or another. All languages I know of are based on something like sequences. We use them for programs. They're used for websites and XML documents, which arguably websites should be, right? They're also in our body in a way, even though maybe encoded in a slightly more wet and yucky form, but DNA sequences that make up your genome are also strings in essence. And of course, bit strings, so when we get closer to computers, everything is ultimately somehow bits, and main memory is one. We think of it as one long sequence of bits. And so everything you do in a computer ultimately is a string if you want to look at it that way, because it's a sequence of bits. Although sometimes a bit more structure is imposed on these. But this also means there's many different applications, also many different tasks and questions we want to ask about strings. So there's a lot of different things we can do with strings. And so this will keep us busy for a few more weeks. In this first unit, we'll look at finding in one long string, which we will call the text. We'll try to find a pattern. And the pattern is really just another string. So think of finding all occurrences of whatever, love in the works of Shakespeare. Might be one example. Another more esoteric one is finding a certain gene that's encoded in your DNA. You want to find if that gene is present in your DNA. That used to be science fiction, but it no longer is. You can ask a company to sequence your DNA, and they will get back to you with a 2 GB text file. And then you can do all these analyses if you can make sense of them. Yeah, virus scanners are usually based on something like finding specific patterns. They're often, at least the basic form is quite dumb. It's trying to find specific pieces in code that it knows are part of viruses. They can do more sophisticated things as well. Finding patterns like this is often a building block for other applications. For example, in bioinformatics, if you're talking about genomes, you often need slightly more sophisticated notions of finding strings. Usually things are not exact, but there's slight variations that are essentially irrelevant for how your body works. And now the promised notation. So bear with me for a second. Strings have an alphabet. We always, when we talk about strings, we always need to assume we know what are the possible characters that can occur. We assume that this is a fixed and finite set. So it's not like all positive integers. It has to be fixed. And so we can speak of little sigma, the size of big sigma, the size of the alphabet, the number of different characters. Now, if you think about English, you might think, okay, we have 26 letters, but then we have them in lowercase, capital, and uppercase, and we have all the punctuations and spaces, etc. So we probably have a few more characters to take care of. Traditionally, I think we'll talk about this in a second. So you know ASCII, this character encoding that has 128 characters that is usually enough for most Western European languages and English, for example, but already struggles with some like German because we have a few other characters that are not represented. So even there, you have not just the 26, but something like 100 characters. And this has recently been, or more or less recently been extended massively. So you now have Unicode with all the emoji, they all count as a separate character. So we have many, many more. I lost track. I think Unicode has around 150,000 characters. That's just something to bear in mind. So this sigma can be really small. It's 4 for DNA, 4 different nucleotide bases. But it can also be hundreds of thousands, depending on what the application is. All right, here are the nucleotides for DNA. Now, an alphabet tells you what a single letter is. A string is several letters. And we can write this as the Cartesian product of the alphabet. So it's just a string of 2 characters is a pair of 2 characters. Or in general, a string of length n is an n-tuple of characters. And that's the way to write that in mathematical notation. So you can write sigma to the n if you know the length is fixed. Then in this context, 2 other notations are often handy. The star means any length we don't know, including 0, so the empty string, which is this Greek epsilon. That's just the string of no characters of length 0. It's sometimes useful to be able to write that down without writing nothing. And sigma plus is, well, similar, but starts at 1. We will massively make use of the fact that a string is a sequence and we can access characters by index. And so we'll just write this like this. So other books or other lecture notes will vary the notation there. But I think it's convenient to not hide the relevant thing in the index, the subscript. So we use this array notation to access strings, and many programming languages represent strings as arrays of characters. So this is close to their implementation as well. And again, we started with 0, like all arrays in this class. So if a string has length n, it has indices 0 up to n minus 1. We'll just write 2 strings after each other for their concatenation, so just putting one string behind the other. And if you want to spell it out, you can use this multiplication symbol. And the last thing is this notation that we've used for sorting, for recursive calls of sorting algorithms already, so it's not really new. This is a slice of a string from positions I to j. So in this notation, including the endpoint, this notation will often be convenient as before for sorting. You know this already. So I is inclusive, j is exclusive. So any such thing is just called a substring of a string. Be careful. I will try to be consistent that a subsequence is something different. A subsequence is where I can take any positions as long as they're left to right, but I can leave out things in the middle. Whereas a substring is a contiguous subsequence where there's everything included from an endpoint, beginning point to an endpoint. Okay. And two more vocabularies is prefix and suffix. Prefix is something that a substring that starts at the beginning. Suffix is a substring that ends at the end. I think that's it. So time to wake you up, as always. Where do we have this? There. This can be a quick one. It's just testing if you paid attention. We need a few more votes. Even though it looks like a fairly clear result. Okay, 3, 2, 1. All right, we have a clear majority for true. That's correct. So remember, sigma star is a string of any length, including the empty string, so including length 0. Sigma plus is all strings of any length, but starting with length 1. So if you want to get sigma star from sigma plus, you just have to add the empty string again. Note that the empty string is kind of the only string where we don't have to obsess about its alphabet. It fits for anything because it has no characters anyways. All other strings should have a properly defined alphabet. The last part for this introduction and this massive list of notation is the formal definition of what the problem is like that we're looking at. So string matching. As I said before, the problem consists of two inputs. We have a text t, and now the text will always be of length n, or n will always be the length of the text. And p is the pattern that we're trying to find, which is some other string over the same alphabet. Note that they have the same sigma. And the pattern has length m. Now, we usually think of the pattern being relatively short and the text being relatively long. Formally, that's not part of the problem. It's just usually the case. Now, if the pattern is longer than the text, we don't have to search. But the pattern could be half the text, something. That's not unthinkable, but usually you can think of the pattern being small. And so for the output, it's a little, there's different variations. And I want to stress here that we find the first occurrence only for this point. So we try to find the smallest position, I, so that if I take the substring of t starting at position I find the pattern. And I take the smallest such I, so it's the leftmost occurrence, the first occurrence of this pattern in the string, in the text. If you want to find all occurrences, you can always find the first and then remove that occurrence from the string and then start the search again on the remainder. That's usually not a problem. There's another option. If the pattern does not occur at all, we return some special return value. I'll just write return no match in the pseudocode. Different programming languages have different conventions, what's convenient there, so we'll keep it abstract. A variant of the problem, as I hinted at, is to find all occurrences. We'll talk about this at some point, because for some of the algorithms, you can find all occurrences in essentially slightly faster than searching for the first and then continuing from there. Because you kind of give up some information you learned already. But for now, we'll focus on always finding the first occurrence. Okay, let's do a small example. Here's a string. Where is he? If I say the pattern is he, I want to find where is the first occurrence. Don't be tricked. The first occurrence is here. There's a second occurrence, which is a bit more springs to the eye, but so the return value here would be 1. Remember, we start at 0. And if I search for who, I get no match because it doesn't occur. I wanted to stress that programming languages tend to implement this because it's a primitive. They don't always implement it in a very smart way. Maybe we'll come back to this. So in Java, there's a class string, and it has a find index. It has an index of method that finds in the first occurrence. And in Python, it's called find. Okay, and I'm confident that any other programming language you come up with will have an implementation of string matching too. Okay, one more practice round. It's not even strictly speaking about string matching, it's just practicing the notation again. I mean, pay close attention to the types of parentheses. Other than that, there's no tricks. It's just, I know, counting is hard, and then it's Monday. Okay. I see reasonable things coming in. Three, two, one, and locked. So I guess it's kind of clear, although some people sent no idea. So let's go through this very briefly again. If I had shown you this, it might have been a little more convenient. So here are the indices on top of the characters. And now you just start at the 3rd position, but counting with 0, and then up to 7, but excluding 7, so it's up to 6. So COMP526. Okay. Easy enough. Shall we do some real algorithms?